For linear transformations in 2 dimensions, we require a 2 by 2 matrix. Each column of the matrix can be thought of as transforming where the I and j standard basis vectors go. This one concept is probably the most important thing to remember for understanding transformation matrices. I is the vector x equals 1, y equals 0, so it corresponds to the unit vector on the x-axis. A unit vector simply means the length of it is 1. The j vector is the unit vector on the y-axis, therefore it has the coordinates 0, 1. Okay, so the basic idea is that the I and j vectors get transformed to the coordinates specified by each column of the matrix, and that the entire space gets stretched and rotates with them. In this video, I'm going to focus mostly on how to apply transformations and less on understanding the underlying mathematics. We will leave all the actual computation details to the GLM library. For more detailed explanations of the mathematics involved, I've provided some great resources in the video description. So let's start by opening the fragment shader and adding to the push constant layout a new field of type mat2 called transform. mat2 is a built-in type in the GLSL language representing a 2 by 2 matrix. There also exists a mat3 and mat4 type for 3 by 3 and 4 by 4 matrices respectively. Next, in the vertex shader, I will also add the mat2 transform field, and then update the GL position calculation to multiply push.transform by position. Note that order here matters. Unlike typical multiplication, multiplication using matrices is not commutative. This means that push.transform times position is not equal to position times push.transform. Then in the app implementation, we need to update the simple push constant data struct to match the shader. So add a GLM mat2 transform field, and I'll default initialize it to the identity matrix. An identity matrix has 1s on its main diagonal and 0 everywhere else. This is typically denoted by a capital I, and any vector multiplied by the identity matrix is equal to itself. So this is just like how any number multiplied by 1 equals itself. Note that this constructor for a GLM matrix takes one number and it initializes just the main diagonal, not every entry in the matrix. Now, if you build and run, everything should be the same, but now behind the scenes, every vertex is being multiplied by that transformation. For now though, the transform is just the identity, so it has no effect. Next, we're going to create a gameObj header file. I'll call mine lve gameObj.hpp, and add a header guard pragma once, followed by your namespace, so in my case, namespace lve, and then class lve gameObj. Typically, a game object is anything in the game with a collection of properties and methods. For example, in Mario, your character, the warp pipe, Goomba 1 and Goomba 2, and so on would each be a game object. For the start of this series, I'll be using a very simple object model to represent game objects. Simply put, everything will be an instance of this one gameObj class, which will consist of each property that the engine has, regardless of whether or not that gameObj requires those properties to function. So for example, a Mario gameObj may require a property that tracks Mario's current power-up status, be it a mushroom, fire flower, tanuki suit, and so on. However, using this system, even the Goomba gameObj would have this property, even though it will never be used in the program. Of course, this is extremely inefficient as the game grows in complexity and more component types are created, but it's quick to implement and maintains maximum flexibility, which is great for us right now since we will often be changing things and prototyping different features. I feel obligated though to at least mention some alternatives right now. An entity component system is really the way to go in my opinion, but object-oriented designs exist as well. Each have their own advantages and disadvantages. I've included 3 resources in the description below. The first explains game object models and provides an example of object-oriented design. Next is an old iOS tutorial, but it explains well the concept of entity component systems and different ways they can be implemented. And finally, this tutorial by Austin Moreland goes through his C++ implementation of an ECS. I really like this implementation, and it is very similar to what I plan to eventually implement down the line. So each game object will have a unique ID. So add a public type alias using ID type equal to unsigned int. Then add a private ID type member variable called ID. Now to ensure that each game object will be created with a unique ID, we're going to make the game object constructor private. So lve game object, ID type, object ID, and a member initialization list to initialize the ID variable with object ID. Next, add a public function, static LVE gameObject called createGameObject. And in its body, declare and initialize a static ID type variable called currentID equal to 0. Then return an LVE gameObject initialized with the currentID++. Make sure not to miss adding the increment operator here, otherwise all our gameObjects will be created with the ID 0. And then add a getter function, ID type getID, that simply returns the gameObject's ID. I'm going to delete the copy constructor and assignment operator because we want to avoid having duplicate gameObjects. But I'm going to enable the move constructor and assignment operator to use the default. Next, let's start adding some properties to this gameObject class. So include lvemodel.hpp as well as memory from the standard library. Then I'll add a shared pointer with an LVE model just called model, and then a GLM vec3 member called color. Next, I'm going to define a new struct called transform2dComponent and add a field GLM vec2 called translation. This will be used to move objects up, down, left, and right. Also add a new function GLM mat2 called mat2. That for now will just return a 2x2 identity matrix. Finally, let's add this transform2d component to the gameObject with a new member variable called transform2d. Navigate to your application header and include the gameObject header file we just created. Next, replace the LVE model member variable with an std vector of LVE gameObjects called gameObjects. Then you can rename the loadModels function to instead be called loadGameObjects. And finally, let's add a new function, void renderGameObjects, which takes a vk command buffer parameter. Okay, now in your application implementation file, start by renaming the loadModels function call to loadGameObjects in the constructor, and then update the function signature to the new name. Next, add the auto keyword before LVE model since it is no longer a member variable, and change makeUnique to makeShared. This is a good instance to use shared pointers because it allows us to have one model instance that can be used by multiple gameObjects, and it will stay in memory as long as one gameObject is still using it. Then auto triangle is equal to LVE gameObject create gameObject. I'll set triangle.model equal to LVE model and triangle.color equal to 0.1, 0.8, 0.1, which should be a nice greenish color. Next, set the triangle.transform2d.translation.x to 0.2, which will move the triangle slightly to the right. Then make sure to call gameObjects.pushback std_moveTriangle. This is why we needed to default the move operator in the gameObject class. Okay, now we need to implement the renderObjects function. I'm going to scroll down to just below where I have my record command buffer function and add void first app render gameObjects with a parameter vk command buffer. First thing in the function body, I'll call LVE pipeline arrow bind command buffer. Next, loop through all gameObjects with forAutoReference object in gameObjects, and we're going to essentially just update the same push constants but with the gameObjects component values instead. So copy and paste these lines into the for loop, and I'll add update push.offset to equal object.transform2d.translation, push.color to be object.color, and push.transform to be equal to object.transform.mat2 function call, which is just the identity matrix for now. Update command buffers at image index to just be the command buffer arg, and then we just need to call object.model arrow bind command buffer and object.model arrow draw command buffer. Then just above in the record command buffer function, we can replace all these lines with just the call to render gameObjects, with the command buffers at image index as the argument. One last thing is we don't need this local frame count variable anymore, so you can remove that. Build and run your code, and if everything is working properly, you should have a green triangle slightly offset to the right. Now this seems like we've made negative progress, but let's finish implementing our transforms. Scaling along the coordinate axes is perhaps the easiest transformation to understand. We can scale points in the x-axis and y-axis independently of one another. In your gameObj file, add a second member variable to the transform2d struct of type glmvec2 called scale, and initialize the x and y values to 1, 1. Then in the mat2 function, add a glmmat2 local variable called scalemat. The transformation matrix that performs a scale has the following form. The GLM matrix constructor takes each column as a parameter. Emphasis on column, not row. So I have the first column as scale.x, 0, and the second as 0, scale.y. I've kept a list of my worst debugging experiences, and a few years ago while working on a grad level university assignment, I probably wasted about 4 hours because I assumed the GLM constructor took rows and not columns. Anyway, return scalemat and navigate back to the load gameObjs function. If I set scale x to 2 and scale y to 0.5, then intuitively we can imagine the I basis vector at 1, 0 being stretched to 2, 0, and the basis vector j at 0, 1 being squished to 0, 0.5. And as I and j get transformed, they move the whole space with them, including the points on our triangle. Another useful transformation is rotation. So back in the gameObj file, add a float rotation field to the transform2d component struct. The form of its transformation matrix is a bit more complicated to understand, but again the intuition is just to consider where the first column takes I and the second column takes j. If you bust out some high school trigonometry, we can use sine theta equals opposite over hypotenuse and cos theta equals adjacent over hypotenuse to calculate the ending positions of the I and j basis vectors for any rotation angle. A rotation will not change the length of the I and j vectors, so the length of the hypotenuse must always be 1. So add const float s equals glm sine rotation, and const float c equals glm cos rotation. And then we have glm mat2 rotation matrix, with the first column being cos theta sine theta, since those are the coordinates that the I basis vector 1, 0 will land after the rotation. And negative sine theta cos theta for the second column, because that's where the basis vector j at 0, 1 will end up. Update the return statement to be the rotation times the scale. One of the great things about using matrices to represent transformations is that it also lets us combine together multiple transformations into a single matrix, just by using multiplication. Then head to your application file, and at the top of the file, I'll add include glm/gtc/constant.hpp, since we're going to want to use the pi constant in just a moment. Next, in the load gameObjs function, set triangle.transform2d.rotation equal to 0.25 times the glm 2pi constant, and as a float. Don't forget we're using radians, not degrees. And 2 pi is 1 full rotation, so a quarter pi should be a 90-degree rotation. Build and run, and that's interesting. The triangle may have rotated in the direction opposite to what you were expecting. That's just because the y-axis in Vulkan points down, opposite to the convention typically used for math. Okay, now, one big advantage of having this gameObj infrastructure compared to what we had before is that we can easily update an object frame to frame. So for example, in the render gameObjs function, you could add in at the start of the for loop, object.transform2d.rotation is equal to glm mod object.transform.rotation plus 0.01, glm 2 pi. This will continuously rotate the triangle in a full circle. One more thing, always keep in mind that for matrix multiplication, order matters. So in this case, the scale transform is performed first, followed by the rotation. If we reverse the order, we get a different result, which makes intuitive sense if you think about each step occurring one after the other. The order transformations are applied should be read as occurring from right to left. This is because by convention, I'll be multiplying transformation matrices on the left-hand side and position vectors on the right-hand side within every shader. This is known as column major order. For more information, see this article that goes into way more depth than I could explain in a video. This is also a great resource for learning the maths required for computer graphics. So if we first rotate the triangle and then scale it along the X and Y axes, it's a lot harder to intuitively predict the results. So we'll stick with what we had originally. With just these current transformations, you can already create some pretty cool effects. For example, with just a few extra lines of code in the load gameObj and render gameObj functions, I can create this periodic animation pattern. I've included a pastebin link for this code in the description below. Transformation matrices are already incredibly useful, and we've only scratched the surface. Some key takeaways are: the columns of a transformation matrix say where the I and j basis vectors end up. Transformations can be combined using matrix multiplication, and matrix multiplication is not commutative, so multiplication order matters. We also started creating a component-based runtime gameObj model. This is a very simple implementation in that every component is stored directly on the gameObj. This will scale very poorly in terms of memory usage, but is advantageous for creating a prototype engine. Also, thank you so much to everyone who has subscribed. Since the last video, we passed the 1,000 subscriber mark, which is absolutely insane. When I started this series, I really had no idea what to expect, but I am so thrilled by the response. So thank you very much, and cheers.